Okay, so last time, the last class, we introduced the notion of, I mean, everybody can see the slides, no?
Yes, sir.
Okay. Of transition systems, okay, and as a formal model to capture the behavior of programs, the operational behavior of programs. Okay, and we saw that, and the transition system itself was based on, kind of converting the program into a CFG. And the transition system was defined by two formulas, one that captured the initial set of states, and the other that the transition relation that modeled each primitive basic steps that are executed during the execution of a program. Okay, so this CFG is kind of useful when you see how the formula, okay, for example, the transition system was defined by these two formulas. Okay. Yeah, and you notice that this formula that defines the transition relation pretty much has, it's a conjunction of several components each, and it has one conjunct for every transition from possible here. Okay, so that's how it's defined. So in the process, okay, so, and you can see that the execution, the semantics, which is called the set of all executions that are possible when a program is executed, is generated, can be seen as generated by this transition relation. Okay, one, this is not the only way to model semantics of program. There are several other ways of doing it. This particular one, as you can see, it in this translation, the transition system pretty much throws away the structure of the program. Okay, it kind of keeps track of what the effect of the thing is by defining, in terms of a formula, the transition that happens at a very low level. By low level, I mean the single execution step. Sometimes it is, and I also noted the fact that model checking and static analysis, etc., specifically model checking, some tools, they actually derive this transition system automatically, and then enumerate all possible executions and check properties for them. But this kind of modeling, it throws away the structure, and sometimes it is useful to maintain, have a way of defining the semantics that keeps the structure of the program, so that your analysis can take leverage the structure. Okay, one such semantics is what we will see today, called the structural operational semantics. It's operational, it's structural in the sense that, as you will see, it keeps the structure which is thrown away in the transition system model, structure of the program. It is still operational in the sense it characterizes the set of execution traces that are that define the semantics of program, and that's what we will do today. Okay. Yeah, so it's kind of, it considers a low-level description of the semantics, are useful, for state explorations and model checking, and sometimes, but sometimes Not so for formal proofs, or even for certain kinds of model checking techniques, maintaining, especially for software, maintaining some of that structure would be useful. So it is useful for you to understand the structural operational semantics, okay? Because model checking and abstract interpretation can be considered as automating these search for these formal proofs. So in the beginning, what we'll see is I'll give you a brief feel for how these semantics system can be used to derive formal proofs. And after that, before we move on to seeing how model checking and static analysis automate this search for proofs. So sometimes this kind of semantics is also called small step operational semantics. As I said, it defines the behavior of a program in terms of behavior of its components, parts. Okay, so that's in that sense it is structural, just like the grammar for the program, is defined. A program syntax is defined inductively. Okay, using grammars with terminals and non-terminals. Here, the operational behavior is also described inductively as in terms of the structure of the program. So the SOS specifications take the form of a set of inference rules defining valid transitions of a composite piece of program in terms of the transitions that its various components take. Okay? And then your formal analysis of the behavior program is pretty much doing proofs using these inference rules. So just like in the transition system, we have to keep track of the valuations for the variables. So, and that is done by defining an environment. An environment is a formalization of the computer's memory, which is what the programs change as they execute each instruction in the program. So, and that is, so it can be defined by means of a function which map the variables to some value domain. Okay, and we define what's called an update or a substitution operation on this environment object, which is a function, and that's denoted as sigma with square brackets, x getting a new value v. Okay, and that really is like an update in the sense it gives a new environment, sigma prime, which is identical to sigma except for the value it returns for the variable v. So if y is equal to x, then it returns v, and otherwise it returns whatever is the value that sigma assigns. In that sense, this is just like an update function for the environment. Okay? And just like in the case of transition systems, a set of initial states can be defined in different ways. So there'll be an initial environment. Either you can say that variables can take arbitrary values at the beginning of the program, or you can say that there is a special uninitialized variable called undefined, which you can include as a special constant in the domain that the variables range over, and you can say that right at the beginning that it is mapped on undefined. That's a matter of choice. Okay. Now, like I said, so here the it's completely based on the structure or the syntax. Though the structural operation semantics also define the semantics for evaluation of expressions. Okay, based on its syntax. Okay, so given an expression constructed in the grammar for the program that we saw defined by the grammar, it defines the and given an environment and an expression, it gives the value that the expression evaluates to, denotes under that semantics. And this is defined recursively. Okay, so if your expression is an arithmetic expression where some operation is applied to alpha 1, alpha 2, then you just get the value in that environment, the current value of the left-hand side expression, similarly the right-hand side expression, and then you apply that whatever operation, and then operator is, there is a function that it defines, okay? And it could be either plus, minus, a star, and so on. So there will be the standard functions that these operators denote, okay? So, and similarly, that is for arithmetic expression. Similarly, you do for, you define the eval function for recursively for Boolean expressions. So at the atomic level, so you have when it is a variable, when the expression is a variable, that is at the terminal, then it is just whatever value, its current value as given by the environment, okay? Similarly, if it's a constant, then it is whatever that constant is, like 1, 2, etc. And if it's a Boolean constant, which belongs to the Boolean domain, then it is just either true or false. Okay. So, for example, eval, suppose my environment in arbitrary environment sigma in which x, the variable x, is assigned to true. If I were to evaluate this expression shown here in sigma prime, then what you would get is as expected. So it has to recursively apply to this, since the right side argument is true or something, that just simplifies to true. And eval of not of x recursively goes down and does an evaluation of x, and then applies the Boolean negation operation to whatever value the eval gives, which in this case, in sigma prime, it will be true, right? Because it is sigma prime, updates the value of x to true, and therefore this is to false. Okay, so this is how the structural operation semantics, in that sense, it is built from the using the syntax of things. So any questions here? So have you guys seen this kind of semantic definition in your programming languages course? Any of you?
Yes, and like when we were doing lambda calculus, I think something similar
some
we
of
saw.
you might have taken the lambda calculus course. So yes, okay. So but I guess not all of you would have seen, no? So, so I will, for those that are not seen. Okay. Yeah, and then we have, in this case, in the case of transition system, we just had the state as a thing, and then we had to have a program counter there to keep track of the location. Although there are variants of transition system modeling style in which you don't need to keep exactly keep track of the program counter. So here, since we deliberately want to make it structural, so we define a configuration, which is actually a pair, where the first component is the actual program, and the second component is the current environment, okay, of the result of having executed the program S up to a certain point. Okay, so that is what. So we maintain both the program as well as the environment as the program executes. Okay, so and then we use a special configuration called denoted by the tick mark. Okay, which to denote the final configuration. So this is relevant for programs for terminating programs. So, okay, when you terminate, it'll be a thing. I mean, these kinds of special configurations can be defined to denote error, okay, error state in a program and so on, as we will see later. Okay, so then in addition to that, you'll see the way that we define the semantics. There's a notion of a program being stuck. Okay, so I mean, yeah. So when S is not equal to sigma, they can also be such that it is either you can make progress in terms of the rules of execution that you will see that we will define, or in some cases it can be stuck. Okay, so and this being stuck can be due to evaluation errors, for example. That might be one way to, if you don't want to model errors explicitly as part of your semantics, you can define your inference rule such that none of the inference rules is applicable to a state which can be considered as error. Or you could explicitly model a special configuration to denote the error configuration, and then you can define the semantics such that the error is propagated. Okay, and we will see, and this will be clear when you redefine inference rules. Okay, now before defining the inference rules, I just want to flash the syntax for the grammar defining the syntax for the program. Just to let you know that the structural operational semantics, the way it's defined by means of these inference rules, is done inductively with one inference rule for each of the elements of this grammar. Okay, and as you will see. So there'll be one inference rule for each of them. There'll be some atomic inference rules describing what happens when you execute the primitive commands, and these constructs that build bigger programs from smaller ones will be defined in terms of the semantics for the smaller program. So skip. So given any environment, an arbitrary environment, sigma, skip, after executing skip, it'll, result in this configuration. Okay? Because skip is a primitive command, and you will terminate, and there's nothing more to execute after that. So you will end up, it results in a final configuration without changing sigma. Okay, so that is a way to define that skip is like doesn't do anything, but it does terminate into a final configuration. Okay, please ask questions. Okay, so if you have any doubts, although some of you might have seen it similar to this in other forms, but some of you might not have seen. So don't feel afraid to.
So in the first two, so these are supposed to be inference rules, right?
Correct. So in the first, inference rules, yes, I will tell you if you're not familiar with, if you're familiar with inference rules. Yes. What is your question? Yeah.
So the first and the second ones, shouldn't they have both a premise? And
there are two ways of doing it. Okay. Yeah. So sometimes these at the atomic level, usually, okay. So let me introduce. The inference rule has a numerator and a denominator. Okay, I mean there's something above the line and something below the line. You should read an inference rule as that, assuming that the program so assuming the transition that happens the way that is described by what appears in the numerator, that is above the line, then the program below it will transition into, the configuration below it will transition into the, so assuming that thing, then this will happen. That's how you will have to read it, okay? So, this is the general schema for any inference rules, assuming that this is true. So that is, yeah. So, but at the atomic level, there are two ways of doing it. I mean, you just define what happens, what the configuration that the atomic command yields, okay? And that's what this thing says. So sometimes it's written with an empty numerator, or it can be written like this. I guess that was your confusion. Am I right?
Yeah, so do we assume that if it's an empty numerator, then it's false? And if it's an empty denominator, then it's true?
Let me see. Let me make my... yeah, can you repeat your question?
Yeah, I'm saying if it's an empty denominator, then we assume it to be true.
Yeah, I mean, you don't need to make any assumptions, okay? So, yeah, so, because skip is a terminal command, just like in your grammar. So you define, so yeah, so there's no assumption, correct? No assumption, yeah.
Okay, thanks.
Yeah.
Sir, in the third inference rule.
Yeah, we'll get. Yeah, I'll get to that. Okay. So let's first get through with the first two. Okay. So if it is an assignment command, then assignment command, in an environment sigma, and after the execution, it terminates. Okay. So there's it yields a final configuration. That's what this tick means, and the environment is updated, is a new environment updated with X getting whatever the value, that the result of evaluating E in that environment yields. Okay, so that's what this thing is saying. Is that clear? Okay.
And in this, so E must evaluate to some value, right?
As opposed to?
I mean, we don't know that all expressions evaluate to some value.
Correct.
I mean,
okay, no. So let's assume that, yeah, if whatever evaluates to, okay? So if if evaluates to, so I'm here currently assuming that, so your question, I presume, is what happens if evaluate is not defined for certain expressions, correct? Okay.
yes.
Yeah. Now let's assume for the time being, so then that is for the time being that eval, at least the way that I've defined eval for this particular program, it is complete, okay? So, as we define, okay, in the worst case, it can define undefined, okay? And undefined applied to something will be undefined, yeah? So to that extent. So if you want to model errors explicitly, yeah, there is a way, okay, that you can do. And in this case, we'll say if one of the arguments to any of the operators is undefined, it is undefined, yeah? And then, so in that extent, eval, I'm assuming, is complete, yeah? And if it is not defined, okay, as we will see, we will end up, it may get stuck, okay? Because we are also saying if in the eventuality left certain parts not captured, then that's why we have this notion of getting stuck. Okay, so that you can actually express in terms of that. But for now, let's assume that eval is defines is defined in a complete fashion. Okay, now here So then here, yeah, so this starting the third inference rule, it gets a little more interesting. So you are defining programs that are constructed from smaller components. So this third inference rule defines what happens, the transition, when you execute a program that is constructed, which is as a sequence of two sub programs, S1 and S2. Okay. So what it says is if S1 executing S1 in environment sigma 1 terminates and yields a final configuration sigma. I mean, a final configuration in which with an update environment sigma 2, then this, the result of executing this program, which is the sequencing of S1 followed by S2, is to then apply this inference rule recursively to S2 starting with sigma 2, okay, where sigma 2 is the result of the environment that you get after executing S1. So that's how you have to interpret this. Yeah. So yeah, so that's why I mentioned that this inference rules are inductive. Now, there is also a version of this where, like you said, see, our inference rules are defined such that the new configuration may not terminate. I mean, there might be some more, some smaller programs, a fragment of code that to be executed. And that's why, in order to take care of that, if S1 of sigma 1, see, S1 of sigma 1 can either terminate, in which case you will have a final configuration, or S1 itself can be a more complex program, in which case you may end up, as the result of executing that may give rise to a configuration in which there is a smaller program yet to be executed. So that is the case. This inference rule is applicable to. So if S1 or sigma 1 can also yield some other smaller program sigma 3 with a new environment. If that's the case, then you will have to this S1 with S2 of sigma 1 will yield whatever that the configuration. Okay, so you will have to then replace S1 with S3 with the semicolons S2 in, and you have to evaluate that in sigma 2. And you will see why this is needed, because the way we are defining it in an inductive fashion. Okay.
So 2 questions. The tick is intuitively pointing to the end of the program, is it?
Correct. Yes, that's how I'm doing it. That is the final configuration. Correct.
And the second thing is, this notation only holds for sequential programs, not concurrent programs, right?
Yeah, this is for the program that whose syntax I defined. Okay. Okay. So that's a sequential program. So what is being defined here is sequential semantics. I mean, that's a sequential program. I mean, yes. It's not. I don't have a concurrent operator. Yeah.
Thank you.
Program, yes. Yeah, maybe it would have been better to, but that's okay. So you will recognize, why this kind of S1 sigma 1 can yield another program. Okay. So for example, if then else is some a command which has an expression and 2 sub programs. So and if the eval of B sigma is true, then the result of executing this if then else is whatever that you get. If that eval is true, then you will have to, the result is the result of executing the then part. Okay, and that's what this is saying. If the evaluation of the Boolean condition yields returns false, then what you get is whatever configuration that you get after executing sigma 2 in sigma. You notice that sigma is the same environment as the incoming environment, because evaluation of the expression here does not have, eval does not have any change in sigma. It only reads the environment, does not update the environment. Okay. Sorry about this double equality. That's a mistake. Okay, now it gets more interesting. So how is the semantics of while defined? Okay, so if B is, there are two cases. One where the the while condition, the loop entry condition is true, and the loop entry condition is false. Okay, so if the loop entry condition is true, then what you get is, look at the way that it is defined. So you will have to, executing that while is a result of executing the body of the loop, followed by executing the loop all over again. Okay, so that's what this thing is saying. So that's why this is a case where you see that the transition of execution of a program is defined by appending, making it into a bigger program. So that's why. So you can also get, that's why the relevance of this thing is important. Okay, so because you can, the application of an inference rule over a program can give rise to a configuration in which you will have to execute another program. Okay, so and that's what this thing is saying. So which means that captures the fact that you're repeatedly executing the body of the program until you get to a point where B evaluates. If B evaluates to false, then you have to exit the loop. Okay, which you will. So you will end up reaching a final configuration with sigma, okay, the same environment. So in order to be able to repeatedly apply this thing, so that is where you will have to use this thing. And that's one of the situations where we will end up using that. So given those inference rules, we define what is called a derivation sequence. Okay, a derivation sequence of a program S starting with an environment sigma is either a finite sequence of configurations, sigma naught through sigma k, such that the first configuration is your initial configuration, which you have the program S with the initial environment sigma, and every sigma I is derived by means of one of the inference rules. It's a transition that is derived by the application of one of the inference rules shown earlier. Okay, and sigma k is either a final configuration with a tick mark, or it could be you may end up a configuration where none of the inference rules is applicable. So that's how we have defined it here. Or if you've defined it completely, then maybe there is no stuck configuration. So that's also, so that is stuck configuration is one way to model error. Or it can be an infinite sequence in those cases where say your loop does not terminate. Then you can have an infinite sequence of configurations, a derivation in which the sigma naught is the initial configuration, and for every I greater than or equal to 0, sigma I plus 1 is derived from sigma I by means of an application of one of the inference rules. Okay, So that's how you define. So these derivation sequences are, the analog of a trace that was defined earlier in the case of transition system. Okay. Any questions? We'll see some examples. Any questions so far? Okay. So let's see an example to illustrate what a derivation is for a simple program in this syntax. Okay, so this is a GCD program. It starts, with two variables initialized to 3 and 2, and then it does this loop repeatedly, does either D minus C or C minus D, depending upon whether C is less than D or greater than or equal to D. So this is the loop body, denoted by LB, and this is what while loop, which I consider as GCD. Okay, let's assume, the entire program has these three constructs, but I'm assuming this is just, we start with an initial configuration in which C is assigned to 3 and D is assigned to 2. Okay, so let's see how we can derive, we can apply the inference tools to derive a execution sequence, a derivation sequence for this program. So we start with the program, the entire program GCD, with the initial configuration where C is assigned 3 and D is 2. Okay, and then so here let me get to this. Okay, I hope this is big enough for you to read, because I want to refer to which inference rule that is applicable. Do you need? Yeah. Okay. Good. So from here to here, so GCD is a program that starts with a while construct at the top. Therefore, what is applicable at that point is this inference rule corresponding to the while command. Okay, and which one is applicable? Anyone? Which of these two while rules is applicable at this point?
I think the first one on the second page.
The second page. Okay.
SOS 3.
Yeah, because the condition evaluates to true. C is not equal to D. Therefore, this the precondition, the assumption for the first rule triggers, correct? So therefore, that is replaced, as you said, with S being modified to LB GCD. Okay, that's what this does. All it does is it yields a configuration in which you want the body to be executed once and then execute the while loop. Okay, so that is the application of the first rule for the while. So now here, now you will have to at this point, what do you have to do? So it's a program with a semicolon sequence operator. Therefore, this rule will have to be used, one of these two things. Okay. Okay. So in this case, result of executing S1, since it is just an assignment statement, you first do this and then use the third inference rule, and then you go recursively into the inference rule corresponding to the assignment statement, and that's what that yields this one. Okay, actually, this is what is applied here, the fourth inference rule, and then you get C minus D, and then you use the assignment command and so on. Okay. So then as a result of executing the assignment command, your sigma gets updated. Okay, and that's what happens here in this step here. Okay, so where C you do Yeah, and actually, yes. I mean, there is a, yes, okay. Actually, it is not this one. It's, there is an application of if then else rule, okay? And that's what yields this, okay? So I might have skipped a few steps in here, which then yields C minus D. Yeah, so you have to apply the if then else rule, and then you get C minus D, and then you apply a semicolon and so on, okay? So to get to a GCD, so finally you end up applying the assignment rule, and you get which changes the environment, and then so you keep doing that. So that's how this thing happens. Yeah. So and finally, when C get to a point when C is not equal to D, I'm sorry, C becomes equal to D, you get out. Okay. To and then you terminate, okay, yielding a the final configuration in which C is equal to 1 and D is equal to 1, which is the GCD. So that's what yeah, so you get. So I mean, here's an example of a stuck thing. Okay, see, I'm here. I'm kind of abusing, although strictly speaking, our program does not allow such an if then else. Let's for a moment assume that we also include if then, without an else in our program. Then, if you do not have an inference rule corresponding to if then, so right now we only had defined the semantics for an if then else, where if then else, which had both the then and the else, then you would get stuck. Okay, so that's an example of a stuck configuration. Okay, so if you're not, that is one way. I mean, which means that if you have missing inference rules, then that means that either your semantics is incomplete, okay, or you can sometimes cleverly use this to denote some error situation. So that is what I would call as a stuck configuration. But it is always desirable to define your semantics in a complete way, even if that means that you will have to model the error configurations. Okay, so I'm going to show you how that can be done here. Okay, so yeah, so let's suppose that we want to do an error. See, this using stuck configuration is a lazy way of maybe taking care of errors. Okay, so in order to completely model it, then you'll have to do define inference rules in all to model all the error situations. Okay? So let's see how we can specify as an illustration to specify an error corresponding to division by 0. So we will add a new configuration, just like we had a tick mark to denote a final configuration, to denote terminating configurations. So we'll add an error thing. We'll call it an error configuration. So for example, yeah, earlier there was this comment by what happens if either evaluation of expressions yield error. Okay, so maybe this is a situation. If the second argument to a divide operator is 0, then you want to tag that as an error. Okay, and I suppose that this symbol, the striking symbol, is captures that situation. Okay, and then yeah. So the other one is 0. So evaluation, if E2 is not equal to 0, then it evaluates correctly. So we need to use this special value denoting a division by 0. Okay, that is kind of an error situation at the evaluation level. This can then be used to capture an error configuration, which results while executing a program, and then can be used by extending inference rules. Okay. So to detect the error configuration, then we'll have to add more inference rules while you execute the different programs. So if these are the anytime you in a command you have to evaluate an expression, then if that yields an error, then you transition the program to this error configuration. Okay, and that's how. So you can capture that using these inference rules. So is this clear? Any questions here? Okay. Yeah. So then the missing else can then be captured. Okay. So if you allow an if conditional statement with a missing else, then you will have to ensure that the Boolean expression does not yield to evaluate to false. So if it does, then you can take that program to an error configuration. Okay, so that's a way to catch it. And then you will have to you'll also have to have a rule to define what happens when you when you have what is the result of executing a program in an error, starting with an error configuration. This is like propagating the error. So if executing a part of a program yields an error configuration, then you will have the other things propagate that error. So that way, so this will ensure that once you get an error, the error gets propagated all the way through. Now remember that we had, we could also use this to model assertion. So earlier, although this is not included in the in my syntax, but we showed that in order to verify programs, you would include properties that you want to get verified as assertions. And if you want to model assertions as assertion failures or error, then you can even define an inference rule. So the moment there is an assertion, so the result of executing an assertion is you check if the assertion, a Boolean condition corresponding to the assertion yields false, in which case you can say there's an assertion failure, and you tag that as an error. So with this, you can see you can capture errors, both kind of inherent errors or user-defined property errors with assertions. Okay, so some of the properties that you can verify. Okay, these are some program independent. Okay, design independent properties. So for each configuration, there is at most one successor configuration. Okay, so because if it's a sequential program, usually you would want determinism. Okay, someone asked if this was capturing if it's a concurrent program semantics or a sequential program semantics. So I said the inference rules would define in such a way that it captures sequential semantics. If you added a concurrent program construct, then in that case, so if it's a sequential program, this is a property. Your inference rules will have to be such that there is, your program execution will be deterministic, in the sense that from each configuration, execution of a program in each configuration will yield exactly a unique next configuration. Okay. So you can then, state and analyze properties, such as absence of blocking. If you want to show that my semantics is such that it captures all the behaviors, then maybe you want to have a thing that you will, that you want programs to terminate, okay, with the final configuration. Then you may want to ensure that that nothing is blocked, okay, for each configuration S and sigma, for any configuration for any program with any given sigma, it will not yield something which is not a sigma at the end of execution. Similarly, you can have program-free assertion failures. You can express using, once you define the semantics, then you can formally state these kinds of properties that the program is free of assertion failures. And the way that you will have to do that is, like I pointed out in the case of transition systems, that we'll have to ensure that an error configuration is never reachable, okay? So, and that's similar to here. So for every initial configuration sigma that is consistent with our initial assumption. So every derivation sequence starting with a sigma does not contain the error configuration. So that's what you will have to ensure, okay, either through proof or through automatic analysis methods. Okay, so these are the kinds of properties, okay, that we are interested. Okay, now the semantics that I have developed here. So later we will see, we will develop. I'll introduce a logic called core logic. Okay, just to give you a teaser. Okay, although that is not the main subject of this course. Just to see that you can either ensure prove these properties manually using certain specialized logic and techniques. One such logic is called core logic. Okay, so we will just see. I'll spend 1 or 2 lectures on that for you to get an idea of how to construct proofs. The reason that I wanted to use that logic is because underneath, even what static analysis and model checking does is you can say that is those techniques are automatic way of proving such properties in a completely automatic way. Okay. Just to give you an idea, so how would you prove these properties? So you see, we took quite a bit of effort to introduce this structural operational semantics. What was it? I hope you understood the difference, the main difference between a transition system and the structural operation semantics. That the configuration now has the program component. Okay, the idea for doing that is so we could use in our proofs the structure of your program. We can maybe construct a proof that for a program in terms of by composing proofs of smaller programs. Okay, and to see this, let's suppose one of the things that we might want to prove for the GCD program that we saw earlier was that given any configuration, it always ends in a final configuration. I'm just saying it terminates. Okay. So if you want to prove it, just to give you an idea, and see, in general, if you do not have automated methods, you will have to use what is called structural induction. Okay. So as I just now mentioned, one way to prove it, if you want to prove it mathematical constructed proof. For example, what you can prove is, you know that GCD is a program that has a while loop in it. So while loop will result in, so you can actually prove it inductively. Suppose your body terminates, okay, every time you execute a body LCB in some environment, sigma 1 terminates with an updated environment, sigma 2. And if you're, so you already know that, so after executing, some number of times, your program terminates. Then when you execute execute the body one more time, then it terminates. Okay, that is one way to prove. So that if you're able to, this is like an inductive proof. Okay, so if you had which uses the structural induction on your program to do it, and that's what your structural operational semantics allows you to exploit. Okay, so, and that's why I call this thing as proof by induction. So you can construct a logic which allows you to construct such inductive proofs, but at the core, model checking and static analysis can be viewed as a way of automating such proofs by inductive proofs. That's one way to view this thing, and we will see how this thing is happens. You may not see the actual proof when we discuss model checking and the thing, but in Horde logic we'll first see a little bit of how you can construct proofs, and then we will move to studying model checking techniques in a more algorithmic fashion. Yeah.
So I have a question.
Yeah.
Suppose the program actually does not terminate, then how will the proof should also not terminate in that case, right? I mean, it may be that the proof does not terminate in some situations. So how do we conclude?
Yeah, I think here. Yeah. So you see this, then you won't be able to prove this. Okay. Okay. See, proving halting problem is undecidable. Okay. So all I'm saying is here, if I'm able to prove, given these two proofs, okay, I'm able to prove this, then I know that my program, GCD original program, is terminating. Okay. So what you're asking is, how do I prove non-termination? I guess that's your question, correct?
Yeah.
No, there's no proof. No. Halting the fact that this is a sufficient condition for proving termination. So, see, if you're able to prove in all cases whether program terminates or not terminate, then the halting problem is decidable now. Okay.
So you're saying that it's complete in the sense that if I can derive the proof, then it terminates. And if it terminates, then I can derive the proof. But it does not.
But this is a way to, so your thing is, no, the proof can still be finite, okay? The proof can still be finite. For example, I haven't shown the details of this proof. In order to show this itself, you will have to show that something, that after I do this, something is getting smaller and smaller.
Yeah, exactly. Yeah.
So this proof, in proving this, it'll involve proving that something is getting smaller. Okay, and that is what is used here. Okay, so so that will have to be exploited in doing that. And that's why I said that if you're not able to establish this, then it means that it doesn't mean that it is not terminating, but it is just you're not able to prove that it's not, that you're not able to prove that it is terminating. Yeah.
Yeah.
So,
Yes.
yeah, so you can have finite proofs to show termination. Okay, that's all. That's all I'm saying. So you don't. It's not necessary. I mean, you can still prove non-termination, or I mean, you can prove termination. Okay, you know, so whether you can prove that it is infinite, maybe you can prove that thing too. Okay, that's something you know, you always get a new configuration. Okay, so that is one way to prove non-termination. Okay, so you will never have, you know, but whether you can do it for all programs is the inference rules allow you to you know, conclude you know, termination, non-termination in all cases. That's what I'm not guaranteeing. Yeah. So this is inference rule to prove termination. So if you are not able to do it, then maybe, you know, in order to prove that it is non-terminating, maybe you will have to have a different kind of argument. Yeah. So that's all I'm saying. Yeah. Yeah, I think the first, yeah. So what we did so far, okay. So we introduced a program. I mean, a simple toy programming language, mainly to give you a you know, to introduce this you know, to what program semantics is. Okay, because the correctness of all model checking and static analysis, they are correct in the sense when they really say yes, if this is a property is proved, or no, the property is not proved, it is you know, it is according to that formal semantics. So you need to understand the formal version of the semantics, so which is what we did by means of transition systems, and a control flow graph was just a simplified way of denoting the syntax of the program. We also saw another way of defining the execution semantics, that's operational semantics for the program, which was defined in terms of the structure of your program. So what my roadmap for the next few classes is this. I will publish a detailed schedule of lectures by next class, okay? But at least for the next few class, we did program syntax and semantics. But before we introduce for logic, you know, for some of you who have not had logic, okay, courses, at least, you know, today we have a smaller crowd of 6 people. Let's see who all have shown up. Okay, so 1, 2, 3, 4, only 4 people today. Okay, other than Diganta. So all 4 of you have had logic, I presume? Dhruv?
No.
Yeah.
Okay. Who said no?
Siddhant.
Oh, Siddhant, you haven't said. How do you find the discussion so far? Are you able to follow it?
Yeah, so far it's fine because like inference rule and all, I think we saw in the PLC course. So,
okay. So okay, so that's in that sense. Okay, so that's why, you know, when I do whole logic, so that will involve kind of how you define these inference rules in a slightly different way, you know, as though you're doing it in logic. Okay, so here it was the inference rules, you know, were easy to understand in terms as executing. Okay, executing each programs, whereas there is another way to define. When you define inference rules in logic, it is slightly different. It's as though you're constructing a proof, okay? And that is what core logic introduces. For that, you need to understand, you know, before that, I will do a recap of logic, okay? So what, and then you will see inference rules, etc. in my logical recap. That will be about two lectures and 3 lectures, so that hopefully when we get to whole logic, this will you will be comfortable with that thing. But as I said, understanding model checking and abstract interpretation, which is another term for static analysis, having a peek into these logical concepts would definitely enhance your understanding. But it is not, strictly required. Okay, you'll not be constructing proofs when you when I describe these model checking techniques or abstract interpretation. Okay, but understanding these concepts is important for you to kind of, when I raise this question, why is this algorithm, or technique that I'm describing, an algorithm for this thing, is doing the right thing. Okay, if you want to reflect on that, then understanding what it means for a program to execute will be important, and that's why I'm covering this. So this will be like maybe 3 to 5 lectures. So if you're not if you haven't attended the logic course, then I think you should. Even otherwise, I think whole logic might be something new, and the way that I define my notation, etc., that might be useful for you to attend, even if you've taken a logic course. Okay, so I will end there. Unless you have questions, I've already gone past my time. So if you don't have any other questions, then I will